Good morning, friends. Myself, Bhanvase SU, Department of First Year Engineering, SVERI College of Engineering, Pundrapur. Today we are going to see a presentation on matrix. The content of today's presentation is basic operations on vectors and matrices, linear system of algebraic equations, matrix, rank, existence of a solution, inverse of a matrix, determinants, eigenvalues and eigenvectors, some special types of matrices, symmetric, q-symmetric and orthogonal matrices. Okay, now let's start with the first part of our content, that is matrix. Simple, we know that matrix is a rectangular arrangement of numbers or functions in horizontal and vertical lines. The horizontal lines are called rows and the vertical lines are called columns. The elements of the matrix represented by a letter small a with the subscripts can consist of numbers, variables, functions of variables. And next, a matrix consists number of elements is m into n. M, that is number of rows, and n, that is number of columns. Suppose a 3 by 3 matrix is there, that means the matrix consists 3 rows and 3 columns. Therefore number of elements are total 9 in that matrix. Next, now we will see vectors. What is meant by vector? Vector is a simply matrix with either one row or one column. A matrix with one row is called a row vector, and a matrix with one column is called a column vector. A row vector can be changed into column vector and vice versa by taking the transpose of that vector easily. Consider if A is equal to 3, 4 or 5, that is my first row, then its a transpose is given by 3, 4, 5. Similarly, A is called a row matrix or a row vector, and A transpose, its transpose is called column vector, or we can say column matrix. This is the simple definition of matrix and vector. Now we will move further. Next we have to consider the algebra of matrices, that is summation of matrices, that is addition of two matrices, subtraction of two matrices, scalar multiplication of two matrices and multiplication of two matrices. Now first we will go with matrix addition. Matrix addition is only possible between two matrices which have the same size. Same size in that means same order, that is m by n, 3 m by suppose first matrix having order m by n, the second matrix should be order m by n, then only addition of these two matrices is possible. The operation is done simply by adding the corresponding elements. Suppose we are having two matrices A and B. Order of A is 2 by 2 and order of B is also 2 by 2. Then we can add these two matrices. How the addition will done? Adding the corresponding elements of the matrices. That is first element of first matrix with the second matrix first element. First matrix second element A12 add with the second matrix second element, that is B12. Corresponding elements addition. For example, we will consider, suppose our first matrix is 1, 3, 4, 7 and second matrix is first row 6, 2, 3, 1. Then addition of these two matrices will be done by adding the corresponding elements. 1 plus 6, that is 7, 3 plus 2, that is 5, and the last second row calculations, 4 plus 3 7, 7 plus 1, that is 8, and this is our resultant matrix 7 5 7 8. Clearly it is also having order 2 by 2, therefore no change in the resultant matrix order. Okay, now we will move further to consider a scalar multiplication of the matrix. Scalar means a simple any number, we can say any non-zero number. If you multiply some number to the matrix, that means that we have to multiply every element of the matrix by that number, by that scalar, we can say. Let's consider one simple example. 5 star, that is 5 into the matrix 1 3 4 7. What it means, suppose 5 is that is 5 is a scalar, multiplying to the matrix means every element of that matrix should be multiplied by that scalar. 5 15 20 35 after multiplying by 5. Okay, now let's move further. We will consider the next type of the matrix, that is transpose of a matrix. In many of the problems, the concept transpose of matrix comes. Transpose of a matrix means just interchange rows into columns or columns into rows of the respective matrix. The new transposed matrix is called transpose of a matrix, and its symbol is that matrix raised to in the index we should write capital T. Suppose consider example of 3 by 3, 1 3 8 4 7 2 6 5 0, that is first matrix. Then transpose, suppose we have to interchange column with row or row with column. We will go with the first column as a first row, 1 4 6, next 3 7 8, 3 7 5, sorry, next 8 2 0. This is the transpose, and symbol is a raised to t, like we can say. Okay, next, now we will go one of the important concept of algebra of matrices, that is matrix multiplication. The multiplication of a matrix into another matrix is not possible for all the matrices, and the operation is not cumulative, that is AB is not equal to BA in general. In order to multiply two matrices, the first matrix must have the same number of columns as the second matrix has rows. So if you want to solve for C which is equal to AB, then the matrix A must have as many columns as the matrix B has rows. The resultant matrix C will have the same number of rows as did and the same number of columns as did in B. That is matrix multiplication. In previous slide we have seen how to add the matrices, that is addition of two matrices. Addition of two matrices is possible only if the order of both the matrices should be same, and addition should be the same. Addition should be in the corresponding elements. Now if we consider matrix multiplication, what is the condition? That is, suppose we have to define we have given two matrices A and B, then the product A into B is exist if and only if number of columns of A is equal to number of rows of B, then only the matrix multiplication is possible. And one more thing is that AB is not equal to BA. Like if we consider for addition, a plus b is equal to b plus a. This is exist, but ab is not equal to ba. We'll consider one example also for that. Before that, we will decide what will be the order of the resultant. That is, we have written here, we have considered for C what will be the order. For resultant matrix C, we will have with the same number of rows. How much number of rows? Number of rows of A by number of columns of B. That will be the order of the resultant matrix. Suppose our A is of order 3 by 2 and B is of order 2 by 3, then if you consider A into B, then 2 get cancelled, 3 remains, that is 3 by 3. The resultant matrix will be of order 3 by 3. It consists 9 elements. This is the matrix multiplication of two matrices. Okay, now we will see an example of the matrix multiplication is not a commutative. That is, AB is not equal to BA. Let's consider one example. Matrix multiplication we will see. After that we will see counter example. Matrix multiplication operation is done as follows by the index notations. We have defined here CJK, that is summation over I1 to J1 to N A J I and B J K. Let's consider one example first. Suppose A into B, our A matrix is 4 3 7 2 9 0 2 5 1 6. In addition, at the time of addition, we have seen addition will be done by adding the corresponding elements. But in multiplication, there is one particular way to multiply the two matrices. How the multiplication will done? That is, first row, our first element will be our first row with first column, multiplying the corresponding elements. That is 4 into 2 plus 3 into 1. First row, first column, that is our first element. Now go for the second column, first row into second column with multiplying the corresponding elements of that row and column. 4 into 5 plus 3 into 6. Okay, now same procedure we have to repeat for the remaining rows. Let's consider. Second row is 7 2 and our first column is 2 1. Then the multiplication is 7 into 2 plus 2 into 1, and our second element of the second row is second row into second column, that is 7 into 5 plus 6 into 2. Same process again for the third row, 9 into 2 plus 1 into 0. Next, 9 into 5 plus 0 into 6. If you done your calculations, then you will get the first row as 11, 38, 16 plus 16 and 47 for second row, and for third row that is 18, 45. This is our resultant. What is the order of A? It is of 3 rows, 2 columns, 3 by 2, and order of the second matrix is 2 by 2. 2 get cancelled, remaining 1. Number of rows of first, that is 3, and number of columns of second, 3 by 2. The resultant will be the order of 3 by 2. This is the matrix multiplication. How to multiply? First row, first column, second column, third column. These are the elements of first row, the resultant matrix. Second row into first column, first, second column, third column, and so on. That will be our second row. And the third row will be third row into first column, second column, third column, fourth column, and so on. Multiplication with their respective elements. That is the matrix multiplication, one of the very important concept, that is multiplication we have seen. Now we will consider the linear system of equations. One of the important application of matrices is for solving the linear system of equations, which appears in many different problems including electrical networks, statistics, numerical methods for the differential equations. Before to go how to solve the linear system of equations, try to understand what is linear system of equations. The word linear stands for power 1, a variable having power 1, that is linear system of equations, that is it contains n numbers of unknowns. Okay, now let's consider a general form of a linear system of equations can be written as a11 x1 plus a12 x2 plus and so on. a1n xn is equal to b1. Second equation a21 x1 plus and so on. a2n xn is equal to b2 dash dash a m1 comma x1 plus dot up to amn xn is equal to bm, number of constants which are present on RHS. This is a system of m equations because b1 b2 b3 bn b3 b4 b5 up to bm, m equations with n unknowns which are the x1 x2 x3 up to xn. This is the linear system of equations. If you want to write it in the form of matrix form, that is given by the equation a into x is equal to b, where capital A will be our coefficient matrix of unknowns, that is x1 x2 up to xn, and x is a set of unknowns x1 to xn, and capital B is our b1 b2 to bn. There is a matrix representation of the linear system of equations. That is the system of equations shown in the previous slide. We can write more compactly as a matrix equation. Ax is equal to b. What is A? Coefficients of contains all the coefficients of unknowns variables from LHS, and x is a vector of unknowns, that is x1 x2 x3 up to xn, and b is a vector containing the numbers from RHS. Vector stands for a column matrix, simple we can say. Okay, this is the way to write any system compactly in the form of matrix. Ax is equal to b. Okay, now let's move further. Now try to define one new concept, that is a rank for the matrix. A rank of the matrix is simply the number of independent rows in that matrix. The transpose of a matrix has the same rank as the original matrix. To find the rank of a matrix by hand, we can use a Gauss elimination, or linear dependent row vectors will fall out, leaving only the linear independent vectors, the number of which is the rank. This is the actual meaning of rank, but we'll consider it by another. There is another way, easiest way to find the rank for the matrix. A rank, another definition for rank we will consider. Rank is a positive integer. Then there exists R is a set. We will consider a definition of a rank. A rank is a positive integer. First, at least one minor of order R which is not equal to 0, and every minor of order R plus 1 is equal to 0. That is the definition of the rank of a matrix in the form of minor. Suppose we'll consider one example. Suppose a matrix A having order 3 by 3, then maximum rank for the matrix will be 3, because the highest order minor for the 3 by 3 matrix is the matrix itself. Okay, suppose have suppose the matrix of order 3 by 3 having a rank 3, that means that its minor of order 3 by 3, singleton minor of order 3 by 3 is not equal to 0, means its determinant value is not equal to 0. Okay, now every minor of order r plus 1 is equal to 0 if it is exist. For 3 by 3, if I am saying rank is 3, then there is no minor of order 3 plus 1, that is 4 is exist. We will not consider. Suppose a matrix of 3 by 3 having rank 2, that means that at least one minor of order 2 by 2 is not equal to 0, and every minor of order 2 plus 1, that is 3, the determinant value of the matrix is 0. Remember, a rank is a positive integer, it will not be equal to 0. We have to consider the concept rank for a non-zero matrix. Therefore, minimum rank will be 1 and the maximum rank will be, it depends upon the order of the given matrix. Okay, this is the rank for the matrix. To find the rank for the matrix, we can use Gauss elimination method. Our linearly dependent row vectors will fall out, leaving only the linear independent vectors, the number of which is the rank. Okay, another methods are there. By using elementary transformation, we can convert the given matrix into normal form of the matrix, echelon form of the matrix, and we will obtain the rank for the matrix. Okay, this is the rank for the matrix. Now we will see inverse of the matrix. Inverse of a matrix A is denoted as A inverse. Definition of inverse of a matrix: suppose the product of two matrices A and B exist and it is a unit matrix, that is identity matrix, then A is called inverse of B or B is called inverse of A. That is, by the definition, A of A inverse or A inverse of A is equal to identity matrix I, that is where I is equal to the identity matrix. Theorem: the inverse of n by n matrix A is exist if and only if the rank of A is equal to n. What it states the theorem: inverse of the matrix A is exist if the rank of A is equal to n. A rank of A is equal to n, what it means? There exists at least one minor of order n, that is of matrix itself, matrix determinant value of the matrix itself not equal to 0, because we are saying n is a rank for that matrix. Minor of order n not equal to 0 means matrix value of the matrix value, determinant value of the matrix should not be equal to 0. In other words, we can say for a square matrix, A inverse is exist only if the determinant value of the given matrix should not be equal to 0. That is, in other words, matrix should be non-singular. Hope you have understood. Now, next, another methods are there to find the rank, to find the inverse of a matrix. Gauss elimination method we can use to find the inverse of the matrix by hand, that is by elementary transformation. And the next one we can say adjoint method, that is by using the formula A inverse is equal to adjoint of the matrix upon determinant of A. That is one of the formula to get the inverse of a matrix. Okay, now we will consider the determinant which we have many of the times I have considered determinant. Let's clear the determinant. What is a determinant? Determinants are useful in eigenvalue problems and differential equations. Can be found only for a square matrices. It will be found for only for the square matrices. What is meant by square matrices? Number of rows is equal to number of columns. For such matrices, it is possible to find the determinant. Let's consider a 2 by 2 matrix, 2 by 2 determinant. First row 1 3, second row 4 7. Its determined values exist because number of rows 2 and number of columns are also 2. Okay. And how the value will exist? It is just cross multiplying 1 into 7 and 3 into 4, and after subtracting value we get -5. Clearly determinant has some value. It's 2 by 2 determinant, it has some value, that is -5. Now we will consider a higher order determinant, that is of 3 by 3. The determinant of a 3 by 3 matrix is found as the follows. The terms of RHS can be evaluated as shown for the second order determinant in previous one. Consider a determinant of A. Elements are A11, A12, A13, A21, A22, A23, A31, A32, A33 is equal to, suppose, A11. How to solve this determinant? 3 by 3. Let's consider the first leading element A11. Deleting first row and first column, we get the minor as A22, A23, A32, A33 minus up with opposite sign minus A12. Deleting first row and second column, we get A21, A23, A31, A33 plus A13, that is our first row last element. Deleting first row and third column, we get A21, 22, 31, 32. We know that how to solve the 2 by 2 determinant. Just cross multiply and subtract it, we get the value of the determinant. After solving, we get again a value. Okay, remember the basic difference between a determinant and matrix. Matrix has nothing a value. Matrix is just arrangement of numbers. So, but determinant is arrangement of numbers with some specified values, and it is exist only for square matrices. That is, number of rows equal to number of columns. Okay, now we will move further for some theorems for the determinants. That is, Cramer's rule is there for a system. By using determinant, we can calculate the unknowns, and it is possible only if the determined value is not equal to 0 and the system has a unique solution. Determinant of AB is equal to determinant of BA and determinant of A dot determinant of B. Okay, now let's consider the next eigenvalue and eigenvector. In short, we will consider what is eigenvalue and eigenvector. That A is a square matrix, that is of order n by n. Consider the vector equation Ax is equal to lambda x. A value lambda, which is the equation, which this equation has a solution for x is not equal to 0, then that lambda is called eigenvalue of the matrix. Similarly, the corresponding solution of x are called eigenvectors for the matrix A. Lambda is said to be eigenvalue, it must satisfy this equation, that is, with x is not equal to 0. That is condition for a lambda, and the corresponding eigenvalue should be that corresponding solution for that lambda, that is our x, is eigenvector for the matrix. This is eigenvalue and eigenvector. Okay, now we will consider some special types of matrices. A matrix is called a symmetric matrix if its transpose is equal to original matrix. If you interchange rows into column, if matrix remains unchanged, then we can say it as a symmetric matrix. A skew symmetric matrix is one which A transpose is equal to minus of A transpose, minus of the matrix, given matrix. There is only change in the sign. A12 is equal to minus A21, A13 is equal to minus A13, minus of A23 is equal to plus of A32, plus the diagonal elements, principal diagonal elements should be 0. This is the skew symmetric matrix. And orthogonal matrix, if the transpose and its inverse both are same, we can say that given matrix is orthogonal matrix. Okay, these are some special types of matrices. Okay, thank you friends.